Now that we have a good understanding of, or a better understanding of what a mole is, so again, meaning that number, representing a specific number of things, and atomic mass, or calculating atomic mass or molar mass, let's go ahead and work some more advanced calculations on converting between numbers of things, ions, particles, atoms, molecules, within moles and within grams. So, first example, an aluminum sphere contains 8.55 times 10 to the 22nd aluminum atoms. What is the radius of the sphere in centimeters if the density of aluminum is 2.70 grams per centimeter cubed? Let's visualize what this means. I have some kind of sphere. I want to know its radius. So I'm trying to find R. And I know that this sphere contains 8.55 times 10 to the 22nd aluminum atoms. If I have a sphere, I know volume is equal to 4/3 pi r cubed. I'm trying to find R, right? So R would be equal to V times 3 divided by 4 pi, and I'm going to take the cubed root of that value. So what this is telling me is I really need to find my volume. I know how many atoms I have. I need to use that information to find the volume of the sphere. So let's solve for that first. The volume of aluminum in that sphere. I have 8.55 times 10 to the 22nd aluminum atoms. I'm going to do this all by dimensional analysis because, again, that is the process we want you following, because if you can get your units to cancel out properly, then you're going to be getting the right answer. I don't have a conversion to go from atoms to volume. I don't know. Each atom has a different volume. And so that's based, the only thing I have that can get to volume is density, but density requires grams. I also do not have a conversion to go straight from atoms to grams because each substance, its atom weighs something differently. Like aluminum atom weighs different than an oxygen atom because they have a different number of protons, neutrons, and electrons. Therefore, I have to go through moles. It's the only conversion I have. I'm trying to cancel out my atoms of aluminum. I'm trying to get to moles of aluminum. I know that 1 mole of aluminum contains 6.022 times 10 to the 23rd aluminum atoms. This is going to cancel out my aluminum atoms, and now I'm in moles of aluminum. Now I'm in moles of aluminum, I can go ahead and use the atomic weight of aluminum. Again, that's straight from the periodic table. I look up aluminum on the table, and I see that aluminum has a mass of 26.98 grams for every 1 mole of aluminum. Meaning that if I have 1 mole of aluminum, it would weigh 26.98 grams. I don't have an entire mole, but that's what that first calculation is doing. Here is figuring out how much of the mole do I actually have so I can correlate to the mass that corresponds to that amount. Now I've got grams of aluminum. I can go ahead and use my density. I'm trying to get grams of aluminum to cancel out. Centimeters cubed to go in my numerator. 1 centimeter cubed would weigh 2.70 grams for aluminum specifically. When I calculate this out, I get an answer of 1.43 centimeters cubed. But again, that is just my volume. I want the radius. Now I'm going to go ahead and plug that into my equation for radius. Radius is equal to 1.4. I keep writing 3 there. I don't know why. That should be a 4 too. I think it's because I'm thinking of centimeters cubed. I apologize. Please fix that. That should say 1.42 centimeters cubed. 1.42 centimeters cubed times 3 divided by 4 pi, and I'm going to take the cubed root of that value. If you're not sure how to do cubed root, easiest way to plug this in your calculator is to type in 1.42 times 3 divided by 4 divided by pi raised to the 1/3. All of this in parentheses and then raised to the 1/3, or hit enter and then raised to the 1/3 if you don't have a simple button to undo or to do a cubed root. 0.697 centimeters. Again, this is a cube in here, not a square. This is a cube, so when I cube rooted that brings me back down to centimeters. If I had an aluminum sphere that contained that many aluminum atoms, the radius of that sphere would be 0.697 centimeters. Let's work the next example here. How many H2O molecules are there in 675 grams of H2O? Now, I do have to move this up just a little bit. I apologize if it makes the screen look funky to you. I can't write on the screen when it's too low. But I want to know, I'm going to write down first what I want to know. I want to know number of water molecules. Next, I'm going to write down what I'm given. I'm starting with 675 grams of H2O. To get between grams and molecules, I cannot directly correlate that. I have to go through moles. When in doubt, convert to moles. If you don't know what else to do, try converting to moles. It's probably the correct step. I know that 1 mole of water is equal to the molar mass of water. I have to add up the molar mass. When I look at H2O, I've got 2 hydrogens, so 2 times 1.008 grams per mole, 2.016 grams per mole, and 1 oxygen, 1 times 16.00 grams per mole, 16.00 grams per mole. Add this up, and I'm going to get 18.02 grams per mole because of sig fig rules. Couple questions I get from students all the time. Number 1, how many numbers should I pull off the table? The answer to that is you pull 4 sig figs off the table. Hydrogen, helium, and lithium will all end with 3 decimal places then, because hydrogen is only 1.008, helium, I don't remember, helium's 4.003, lithium 6.940. Okay, so you pour 4 sig figs off. From beryllium up through about molybdenum, technetium, we would pull off 2 decimal places because they all have 2 numbers before the decimal place, and then we need the 4 sig figs overall. Once we hit rhodium, we are over 100 AMU for the mass of that species. We would pull off 1 decimal place. You are never going to be wrong pulling off more. I am only going to pull off 4 because it's most often not going to limit my calculations. The other question I get is oxygen. Depending on what table you look at, you may see oxygen written as 16, you may see 15.99, or you may see 15.9994. Bottom line, if I am pulling it to 4 sig figs, 1, 2, 3, 4, I'm going to cut right there. When I cut there, I have to round up, which is giving me the 16. So most of us just use 16 because that's what we have memorized for oxygen. As long as you're not using your molar mass to limit your calculations, limit your sig figs, you will be fine. So 1 mole of water weighs 18.02 grams of H2O. That has canceled my grams of H2O. Now I'm in moles of water. Now I can go ahead and use Avogadro's number. I know that 1 mole of water contains 6.022 times 10 to the 23rd water molecules. Calculate that out. 3 sig figs, 4 sig figs, 4 sig figs. So I'm going to keep it to 3 sig figs. And I get 2.26 times 10 to the 25th water molecules. Let's look at a couple more. How many moles of carbon are there in 25 grams of carbon? Okay, so again, start by writing down what you want to find. You want to find the number of moles of carbon. Second thing you write down is what your starting value is. We're told 25.0 grams of carbon. It's a pretty straightforward calculation. I have a conversion from moles to grams, right? I know 1 mole, I can go to grams. Like I know a conversion to go from moles to grams. I know a conversion to go, or backwards. I know conversions to go between moles and number of things. I know density is my conversion to go between mass and volume. Okay, these are just some of the conversions I have so far that can help me go through different types of units. I'm trying to cancel out grams. I'm trying to get to moles. Because I'm trying to cancel grams, I have to put grams in carbon in the denominator. If I put it in the numerator, it would not cancel my units. So if anything, if you're ever unsure where to put things, cancel the units first, then put the numbers in. My grams have canceled. I'm going to get moles here, which is what I want. Now I know 1 mole of carbon is 12.01 grams of carbon based on the periodic table. 25.0 divided by 12.01, 3 sig figs, because that 25.0 is 2.08 moles of carbon. This is one of the example questions, though, that's easy for me to check. Does my answer make logical sense? And I like that. In this case, I know if I had 1 mole of carbon, it would weigh 12 grams. If I had 2 moles of carbon, it would weigh 24 grams. I have 25 grams, so to me this makes logical sense that it is about 2 moles, just over 2 moles of carbon. When I'm looking at number of atoms, molecules, etc., I can't correlate those numbers well in my head. They're just really, really big, so I don't see it as well. But when I do get examples like this, I like to fact check myself and say, does that make sense? Yes, this answer makes sense. What about the next question? How many iron atoms are there in 675 grams of iron? Number of iron atoms is what I'm trying to find. And I'm starting with 675, grams of iron. So I need to cancel my grams of iron. And I can't go straight to atoms, but I know I can go to moles. I know I can convert between grams and moles. I look at the table and I see that 1 mole of iron weighs 55.85 grams. Now I'm in moles of iron. I want to cancel my moles of iron and get to atoms of iron. Well, now I'm going to use Avogadro's number. I know 1 mole of anything is 6.022 times 10 to the 23rd of that thing. That cancels my moles of iron, gives me atoms of iron. I calculate this through and I get 7.28 times 10 to the 24 iron atoms. If you are not getting the same answers as these, please come see me for help on your calculator. You're probably plugging something in wrong, and we need you to be able to do this correctly so you're getting your answers right. So another thing we need to think about is multiple ratios. A multiple ratio is telling me how many of one species I have to how many of another. And we should be able to do these looking within formulas or balanced equations. And this is a big part of chemistry, is finding these multiple ratios. 2 places we get multiple ratios: from the subscripts of your chemical formulas and from the coefficients of balanced reactions. What do I mean by that? Well, MgNO3 that is called magnesium nitrate. If I look at this here, what that means is that I have 1 mole of magnesium ions for every 1 mole of magnesium nitrate. Now, we're going to cover polyatomics in the very next chapter, which will help identify how we're splitting these things apart. But right now, you do need to start seeing these a little bit, okay? I could say I have 2 moles of nitrate, because you should already be working on your polyatomics. The 2 down here is applied to the entire thing here. So 2 moles of nitrate for every 1 mole magnesium nitrate. I could say 2 moles of nitrate for every 1 mole of magnesium ions. I know that by writing MgNO3 this represents that I have 1 magnesium and 2 nitrates. I could say 3 moles of ions for every 1 mole of magnesium nitrate, because 3 ions make it up, which means if I have 1 mole of that species, I would have 3 moles of ions. I could say 6 moles of oxygen for every 1 mole of magnesium nitrate, or even let's just say 1 mole of magnesium 2+. That works too. For every 1 magnesium 2+, I have 6 moles of oxygen. We can also get this from the coefficients of the balanced chemical reactions. Now, this is going to come in chapter 4, so just a little bit away from now, very soon, but not quite yet, but from the coefficients of balanced reactions. What do I mean by that? In this reaction, I've got 2 moles of C2H6 with ethane gas reacting with 7 moles of O2 gas, oxygen, to produce 4 moles of CO2 gas or carbon dioxide and 6 moles of water. These are telling me how many of each thing is reacting. That means 2 molecules of C2H6 reacts with 7 molecules of O2 to form 4 molecules of CO2 and 6 molecules of water. But I can scale that up and say 2 moles reacts with 7 moles, producing 4 moles and 6 moles. 2 moles C2H6 to 7 moles of O2. Seven moles of O2 for every 4 moles of CO2. 6 moles of H2O for every 2 moles C2H6. And we can keep that correlation going. We can do any combination. Okay? So let's go ahead and work a couple more examples to kind of try to solidify some of the stuff we just thought about. How many hydrogen atoms are there in 59.3 grams of H2O? I specifically want to know number of hydrogen atoms. I'm starting with 59.3 grams of H2O. I need to figure out what to do next. Well, I'm trying to cancel grams of water, and I'm trying to get to hydrogen atoms. I do not have any correlation between grams and atoms. I do, though, have a correlation for moles. And specifically, I know that 1 mole of water weighs 18.02 grams of water because I've added up the molar mass. I don't want to convert to atoms, though, because this would give me atoms of water. I want atoms of hydrogen. I look at the formula here, and I see that there is 2 moles of hydrogen for every 1 mole of H2O. Let's cancel out my grams of water. Let's cancel out my moles of water. Now I've got moles of hydrogen, which is perfect. I don't want moles, though. I want atoms. I know 1 mole of hydrogen contains 6.022 times 10 to the 23rd hydrogen atoms. That canceled out my moles of hydrogen, got me atoms of hydrogen. I plug that in my calculator and I get, 3.96 times 10 to the 24th hydrogen atoms. What about this one? How many nitrate ions are there in 3.99 grams of aluminum nitrate, AlNO3,3? Now, students start to get overwhelmed at this point because we don't cover naming until chapter 3, which is the next chapter. But if you have this on an assessment, we will either have finished naming by this point, or I would give you the formula, okay? So in this case, I'm telling you NO3 minus ions. In the notes, I just say nitrate, because that's what it's called. You should be working on your polyatomics, though. Number of nitrate ions. If I'm starting with 3.99 grams of aluminum nitrate. I need to cancel grams of aluminum nitrate and get to moles of aluminum nitrate. You add up the molar mass. 1 aluminum, 26.98 grams per mole. This 3 applies to this entire thing, which means I have 3 nitrogens, 3 times 14.01 grams per mole. Again, these are the numbers straight off the table underneath the elements themselves. And then that 3 is applied to that O3 as well, which means 3 times 3 is 9 oxygen, 9 times 16.00 grams per mole. When I add this up with sig fig rules, I'm going to get 213.0 grams per mole. So 9 times 16 brings me down to 1 decimal place because of 4 sig figs. So that's why I have 1 decimal place in my final answer. 213.0 grams for every 1 mole of aluminum nitrate. That cancels my grams of aluminum nitrate, but now I have moles of aluminum nitrate. I want moles of nitrate. I look at the formula and I see the 3 down here. Again, that applies to the nitrate. So I have 3 moles of nitrate ions for every 1 mole of aluminum nitrate. Now I've got moles of nitrate. Now I can go ahead and use Avogadro's number. And of course I ran out of room. 1 mole of nitrate ions is 6.022 times 10 to the 23rd nitrate ions. Calculate this out, and I'm going to get 3.38 times 10 to the 22nd nitrate ions. This next one really throws students off. It's specifically asking me how many ions are there in 15 grams of ammonium carbonate, NH4,2CO3. Again, it will become easier once you start memorizing your polyatomics, but you need to actually be working on those. So if you haven't yet, make sure you start working on your polyatomics because they're quite important in this class. Ammonium carbonate, I see, has 2 ammoniums and 1 carbonate. And again, when you memorize polyatomics, it's easier to split this apart and see it. But there is an NH4 plus, there's a second NH4 plus, and there is a CO3 2 minus. This is called ammonium. This is called carbonate. Overall, there are 3 ions making up this compound, which means there is 3 moles of ions for every 1 mole of ammonium nitrate, ammonium carbonate. That's going to throw students off. Okay, you have to think about what it means. What is it asking? It's not asking for a specific ion, it's asking for ions in general. I want to know number of ions if I'm starting with 15 grams of ammonium carbonate. I'm going to go to moles because I don't have a correlation to go straight from grams, right? I've always got to cancel out my grams here and go to moles. And notice I'm writing what the grams and moles are of because I'm going to be converting between different species. I want to know what I'm talking about. I know that for every 1 mole of ammonium carbonate, I have 96.09 grams of ammonium carbonate. Why do I know that? Well, I look at this formula and I've got 2 nitrogens, 2 times 14.01 grams per mole. I've got overall 8 hydrogens, 8 times 1.008 grams per mole. I've got, 1 carbon, 1 times 12.01 grams per mole, and 3 oxygen, 3 times 16.00 grams per mole, which overall adds up 96.09 grams per mole. So this correlation here, this just cancels out my grams, gets me to moles of ammonium carbonate. Now I can say, well, I know I have 3 moles of ions for every 1 mole of ammonium carbonate. But I don't want to just know number of moles of ions. I want to know how many ions. So for every 1 mole of ions, I have 6.022 times 10 to the 23rd ions. That cancels out my moles of ions, giving me number of ions. Calculate that all the way through, and let's see where I wrote this down. 2.82 times 10 to the 23rd ions. And second question on this slide, how many moles of calcium ions do you have if you have 3.00 times 10 to the 21st formula units of calcium nitrate? Again, formula units is just a weird way of describing the compound because it is an ionic compound. It is the same thing as number of ions. If it was water, we would say number of molecules. It's just the most simplistic way of saying it. The other thing that's cluing me in is this is a really, really big number, so I'm probably going to use Avogadro's number. But you can think about formula units as number of things. So I want to know number of moles of calcium ion specifically. Calcium, again, always +2. It is an alkaline earth metal. It's in group 2, so it's going to be a +2 charge. And I am starting with 3.00 times 10 to the 21st formula units of calcium nitrate. I want to cancel those formula units of calcium nitrate. And I know 6.022 times 10 to the 23rd of those would be 1 mole of calcium nitrate. Cancels out my formula units. I'm now in moles of calcium nitrate. I just want to know how many moles of calcium ions there is. So I need to cancel my moles of calcium nitrate. So I'm going to put that in the denominator. I look at my formula and I see that for every 1 calcium nitrate, I have 1 mole of calcium ions. So mathematically, this last step does not matter, right? I'm not plugging this step here. It does not matter mathematically. I'm not plugging my calculator. However, if you're writing out your work, it is absolutely essential if you want full credit, because you have to show how you got to calcium specifically. You have to show me you understand it's a 1-to-1 ratio. You do it by dimensional analysis. This equals 0.00498. I need 3 sig figs because my 3.00 is 3 sig figs, 6.022 is 4. 0.00498 moles of calcium ions. Students get kind of freaked out because it's a really small number. It is. But remember, this is only to the 21st, and a mole is to the 23rd, so that number actually does make sense. And the last question for this unit. A cereal contains 11.2 grams of sucrose, C12H22O11, per 60 grams of cereal. What mass in grams of cereal must be eaten to consume a total of 0.0424 moles of sucrose? I like this problem because it's kind of incorporating things that we've seen. You're just not thinking about it the way that you would otherwise do it, right? It's incorporating things that we saw with dimensional analysis, but also doing some conversion here. So what is the question telling me? It's actually telling me my conversion factors. The question says, the cereal contains 11.2 grams of sucrose per 60 grams of cereal. That is a conversion factor. 11.2 grams of sucrose, C12O22, or sorry, C12H22, O11, for every 60 grams of cereal. It's then asking what mass in grams of cereal must be eaten to consume a total of this many moles of sucrose. So I want to find the number of moles, the number of grams of cereal. I'm starting with 0.0424 moles, C12H22O11. I need to cancel out my moles, C12H22O11, and get to grams, C12H22O11. Why? Well, I need grams of sucrose so I can use the conversion to get to grams of cereal. I can't convert straight to grams of cereal. I don't have a numerical value for that, right? Please be quiet. I've got 1 mole of sucrose, and I add up the molar mass. 12 carbon, 12 times 12.01 grams per mole, 22H, 22 times 1.008 grams per mole, and we have 11 oxygen, 11 times 16.00 grams per mole. When I add all of that up, I'm going to get a molar mass of 342.3 grams of sucrose per 1 mole of sucrose. It's a pretty big molecule. That cancels out my moles of sucrose. I've got grams of sucrose. I don't want grams of sucrose. I want grams of cereal. I have this great conversion right here, though, right? I was told 11.2 grams of sucrose is contained in 60 grams of cereal. What I need to think about here is I am trying to cancel my grams of sucrose. I am trying to get to grams of cereal. By putting grams of sucrose in the denominator and grams of cereal in the numerator, I'm able to cancel the grams of sucrose and get to grams of cereal. But I have to put the correct numbers in the right spot. 60 grams of cereal contains 11.2 grams of sucrose. Again, conversion factors are equivalency of multiplying something by 1, because 11.2 grams of C6H or C12H22O11 is contained in 60 grams of cereal. So either one can be the numerator. I find when I do the calculation here, 77.8 grams of cereal must be eaten. Let's do a color that we haven't don't have on the slide. 77.8 grams of cereal must be consumed to actually consume 0.0424 moles of sucrose in total.